Well, welcome everybody to the tech talk that I've been wanting to do for like years. And I am here today with John Snyder. And I'm going to give you a little bit of background into this guy because I will tell you something. I've known him a long time. He is freaking brilliant. And if you look up genius in the dictionary, I think your name is right next to it, John. I'm not kidding. Like, you are brilliant. But John is one of our country's leading experts in semiconductor technology development and manufacturing. And so, John, I have to tell you something. When I look at your resume, it's like it's almost make believe because it's so perfect. But even more, I just get exhausted looking at it because the amount of work that has gone into what you have done, from education to your work and life experience. Again, I think I can count on maybe one hand anybody that has your credentials. And so I'm gonna brag a little bit about you if you don't mind, and then you can brag about yourself. But I people need to hear, your background. So you went to West Point, you went to MIT where you got a BS in aerospace engineering. And then if that were not enough, you had to go to Stanford and get your PhD in philosophy and electrical and electronics engineering. Then right out of college, instead of taking a vacation like everybody would, you went immediately to Hitachi developing novel semiconductor devices. Then you went on to National Semiconductor, where you worked on CMOS and sub 100 nanometer transistor architectures. Then, I mean, I'm already exhausted here, John. And then you went on to found Spinnaker Semiconductor Technologies, and you really took a big shot on goal as an entrepreneur. You raised millions of dollars, and the list goes on. So, John, where do you find the energy to do all of this? It's incredible.
Thank you, Daren, for that very generous and I think undeserved introduction.
No, no.
Um, you've really set the standards very high here, so I hope I can live up to it. As far as finding energy to do all these things, you know how it is. It's like anything else in life. If you enjoy what you do, it's not that hard. It's not even work. So I've enjoyed doing all those things that you said. Going to school always came easy to me, and I always did well at it, and always enjoyed it. And so that was actually a great time working in the semiconductor industry and starting a company. Although it had its challenges, had its challenging moments, to be sure. In general, it was a very good time. And I guess I'm kind of spoiled, actually. I'm to the point now where I have trouble doing things if I don't enjoy them. So
Yeah,
I
it's
think by
true.
definition, everything I do is fun and is enjoyable. And sometimes I even get paid for it. Amazing.
Yeah, okay. But and I think there's a point there that you have to follow your passions. And I think you and I are both two individuals that are willing to risk everything to follow our passions, and we're also willing to do the incredible hard work to make those things come alive. And I think one thing in knowing you all these years that I've really appreciated and grown to love is just your innovative spirit. I mean, you're a true innovator. You're somebody that's not afraid to push the boundaries and ask the very difficult questions. And how do we do things better and faster and more efficient? And I think that's one of the things that I've really grown to admire about you, is that you just have this innovating spirit. Where do you think it comes from? I mean, do you feel like this is something you've learned? Is this something that just through your years of education, you just kind of are able to draw on all these different facets of knowledge? What do you think it is? I mean, is this just something in both of our DNA? I don't know. And we're also nuts enough to, follow this dream and vision that we get. But what do you think it is?
I think it's a very good point that you make, that we are the kind of people that are sufficiently unbalanced that we do this kind of thing, and we don't just um, we're not content to um, just collect a paycheck and be done with it. There's a lot more to life than that, and I think we both sort of see it that way, and that sometimes gets us into trouble too.
Oh,
But as far
yes.
as where does that drive come from? I'm really not sure. I'm sure psychologists have studied this question. Where does that innovative drive come from? Not really sure. I don't know what the right answer is. I've always kind of asked why can't, to me, the question of, well, why can't we do things, better or faster, or why is it so expensive, or why does it take so long? Maybe it's an impatience. Maybe we're just fundamentally impatient people, and we want the future to happen now. We want things to be better now, not later. Now. And why can't it happen? And what are the barriers? And it just eats at us, and it annoys us and keeps us up at night. That kind of thing. Maybe that's what it is. Maybe it's a genetic defect that
I think it
we
is.
have.
And by the way, I've never heard it put that way, but I feel like that's what it is for me. I just get impatient. Like I walk into a data center today and I just go, why in the heck are we blowing around hot air? Air is an insulator. It's just why?
Right.
You know what I mean? And it just
Right.
bugged me. And I just see all this energy wasted and pollution, and yet why is nobody solving this problem? And we did. We solved it, right? And it's kind of like you know?
Absolutely.
Yeah, it's
Well,
yeah.
there might be a cultural aspect here as well, where we are, and I think, certainly for me, I think I was encouraged, even as a kid, to think outside the box or ask questions, or just maybe follow the example of my parents who were innovators also in their own right. My mom was in education for many years and was constantly looking for better ways to do things, new ways to do things. Why do some kids do well, others don't, others struggle? What can we do to help them? Why aren't things working? And so on. She was a real innovator in that sense. And my dad as well. My dad was also an entrepreneur. He started a company. He was also in um, the computer industry and electronics, and he tells me stories from the old days of when computers were analog, not digital.
Right.
So I grew up in that environment. I guess it just came naturally, I suppose, and was encouraged.
Yeah, well, I think some of it can be learned, and it certainly is the same for me. I have a similar story as you, and as you know, and um, well, anyway, but I just think that whatever got us to where we both are in life, one thing is we love solving problems, and we really enjoy the impossible, and I think that's what drives us. And so as we move into the impossible, which is some of the things that you're working on now, and in some of the technologies that you've developed, and I think you've been following Gordon Moore's law for most of your career, and I think, as you know, Moore's law predicted that the number of transistors that could fit on a chip would grow exponentially, and he was correct. And I think what is it, every 2 years, the number of transistors will double. Well, we're hitting that ceiling. You're working on things that are going to hopefully get us past that ceiling. How do we improve the performance within computers and chips? And I know we're hitting that ceiling with how many transistors can fit on a die. I mean, what's next? What are we doing?
Well, I think there are many aspects to this problem. There's certainly the one that you mentioned, which is, how many transistors can we fit on a chip? And that actually is still going, is still growing exponentially. It's pretty amazing. We're up to, I think the leading edge chips these days have as many as 20 billion, that's with a B, 20 billion transistors, which is
Wow.
a pretty incredible number. Um,
Now, can I
and
have you
to
pause for 1 second? I have to have you
Sure.
pause for 1 second. So in preparing for this, I just had to go look, and because I just wanted to see what the transistor count on the most powerful chip ever made. Do you know who holds the record right now? It's a company I've never even heard of. Have you ever heard of Cerebras?
No, I haven't actually.
They have 1.2 trillion transistors on a chip with 400,000 cores. I'm not kidding.
Oh my gosh. Okay.
Yeah.
Wow.
Well, anyway, I just read that. So anyway, I hated to interrupt you, but I just had to throw that in there because I was just reading about it because I go, what, how many what is the record right now? And yeah, 1.2 trillion transistors. That's unbelievable.
Well, that's a very impressive number, and that's news to me. I wonder if that chip is in volume production, or if it's just
Yeah, this might be a
sample.
one-off. Yeah. Yeah.
But certainly chips that are in volume production, I think the record is around 20 billion, tens of billions. I think 20, close to 20 billion now in
Wow.
high volume, which is pretty amazing. So we achieve this by um, doing design shrink. So I think we're at the 7 nanometer, maybe it's the 5 nanometer technology node now. So we're getting better we're getting very good at hacking transistors into a smaller area because we can print them smaller. So that's in the two-dimensional realm, but also we expand into three dimensions. We're getting good about stacking die together and connecting them through silicon vias or edge connectors. So we're really very good at that, and that's what keeps the transistor count growing on an exponential curve. There's also another aspect, though, which is just as important, which is the performance of those individual transistors. And what I mean here is the power and speed performance. How much energy does it take for a transistor to switch from on to off or off to on?
Right.
And that number used to be growing exponentially or improving exponentially, but it has, in the last 10, 15 years or so, it has started to level off. There is still some growth there. There are still some improvements being made from generation to generation, but it's nowhere near at the same rate. So we have more transistors, and they perform a little bit better than the last generation. But that's something that needs to be kept in mind. There are actually two separate metrics here, in my mind anyway: the transistor count and then the performance of those transistors as individual devices. And those two factors together contribute to the overall system performance.
Interesting. Now, there's also kind of a, as we look at the chip industry, you have new materials being created. Now you have, materials like graphene, and, you've mentioned a couple of different substances that you're using, like, I don't even know how to even pronounce the word molybdenum. Is it bedendum? I'll let you torture yourself on that one.
Yeah.
Tungsten.
So these are, yes. So this is really my, this is the area that I'm very interested in, is the actual transistor technology itself, as opposed to higher levels of system integration. But down at the transistor level, for decades, the industry has been focused on silicon-based transistors, planar transistors. More recently, transistors that have more of a three-dimensional nature, like FinFETs, and other types of architectures. But some researchers are looking into very novel materials and architectures for next generation transistors. And one popular field that's getting a lot of attention these days are very thin film, monolayer materials, or single digit layers of atomic layers of various materials. Graphene is one of them. These are carbon atoms laid out in a ring structure. Unfortunately, graphene is not a semiconductor; it's a metal, and so it's hard to make a transistor out of it. But there are other materials that also can be put down in small numbers of atomic layers. Molybdenum disulfide is one of them. Tungsten disulfide, and there are some others, but I think those are probably the two most popular. And those materials are semiconductors, so it is possible to make transistors, and some people have actually demonstrated this technology.
So what's that going to mean, though, if when you get these new substances, is it going to increase the speed? Because, like, I mean, I know graphene, for instance, and for a lot of people that don't know, this is kind of the wonder material. It's what they say, strong as a diamond or stronger than a diamond, very thin. It has incredible conductivity. There's a number of different uses, in the computing space for it. But what do these new materials give you that current silicon doesn't? Is it just better conductivity? What is it?
Well, it's the ability, I think, mostly to deposit these layers in a controlled way, in atomic sheets. So you can actually very carefully, through various techniques, you can deposit, one atomic layer of graphene, or one atomic layer, or two or three atomic layers of molybdenum disulfide. And so you get that very, very small dimension, several, literally, atoms, layers of these films that are atoms thick, 3 or 4 atoms thick. And that, the theory goes that should help a lot in building transistors small, or making them small. And that makes sense, that's logical. But there are a lot of other problems that need to be addressed. Specifically, things like how do you make electrical contact to these films? How do you alter their properties through doping? That's a big challenge. So it's not a done deal by any means. It's still a science project in my view at this point. And Well, I applaud the research that's going on in this field. I think we should. One thing that I have learned in my decades of being in the field is to be skeptical. So a lot of new technologies come and go, and they don't make it to the commercial marketplace for any number of reasons. Usually because it's too expensive, or sometimes because there's some fundamental physics problem that just cannot be solved. Like if you can't you might have a wonder material like graphene, but if you can't make a good electrical contact to it, or if those contacts are
That's the
very
problem.
resistive, then
Yep.
it doesn't matter. You don't have a way to access it. So silicon has been our mainstay in the semiconductor industry for since the 60s.
Yep.
And people have been saying for decades that it'll be replaced by, for a while there it was 3,5 materials like gallium arsenide or maybe indium phosphide, but it just never came to pass. And silicon just has too many things going for it. So my prediction is that um, even though we have great research going on and lots, materials being experimented with and new materials being discovered that have amazing properties, at the end of the day, all things considered, it's gonna continue to be a silicon world from here on out. We might do different things with that silicon. We might make it very small, thin. We might confine it in various dimensions to elicit quantum effects and so on and so forth. We might do all that stuff, and people are doing that, but it's still going to be silicon. I think at the end of the day, uh, our computing machines will be silicon based forevermore. That's my prediction.
Well, that's really interesting because I've wondered, and now with the realm of quantum computing, um, you're able to start looking at how can we make different substances. But I think I would agree with you. I mean, there's just silicon has a lot going for it, and at least in the things I've been reading, and um, so this kind of pushes us into kind of another area, which is really about we're moving into this new realm of computing with quantum and all these different emerging technologies. And one area that I think is starting to go mainstream and is very interesting is cryogenic computing. What does this really mean from a chip standpoint and the things that you're working on, and what gets you excited about this field? Because I know it's an area that's of interest to you.
Right. Yes. Well, quantum computing is cryogenic. In
That's
fact,
right.
it's very cryogenic. You do have to get down to the millikelvin, 10 millikelvin. That would be 0.01 Kelvin. So very, very low temperatures to get this to work. And again, it's fascinating technology where they manipulate individual atoms, the electron spin on individual atoms, and manipulate that spin to be either spin up or spin down, um, representing a one or a zero. But the interesting thing about these qubits, as they're called, is that they can also assume any position between a one or a zero. So it's not strictly a binary system. But
And that's
quantum computing,
superposition, right? I mean, so it's really this whole idea of being a zero, a one, or both at the same time. And that's really
yes,
what it's doing.
or
Yeah.
or anywhere in between. It's
Right.
it's a probabilistic distribution of whether the bit is actually a one or a zero, and you can line up many of these bits, and each one of them has their own probabilistic distribution. But what it really comes down to, one of the problems that they face is being able to control accurately or being able to read accurately what those bits are, and that turns out that's a very challenging problem. It's very easy to have these bits suffer what they call decoherence, where they lose their information, and even as something as simple as trying to read these bits can disturb their state.
Yep.
And then you don't really know what the original state was. You only know what the state was after you read it. So there's a lot of work going into managing this decoherence. I think that's what they call
Well,
it.
now isn't it? It's very similar to error correction. So in a traditional world of classical computing, you have error correction when you're doing processing. How do you create error correction in a quantum world with qubits, right? I mean, isn't that really the challenge?
That that is the challenge, and that is a major field of of investigation right now is how do you do this error correction in the quantum realm. Of course, we know how to do error correction very easily in the classical digital realm. All the theory is very well developed and it's very well established in industry, and it works very well. But it can be done in the quantum realm, but it's a much different problem, a much harder problem to
Right.
solve. And from what I've read, it really hasn't been solved yet. There's techniques that involve grouping large numbers of qubits together to form an effective logical qubit. And because there's a large number of these qubits, there's ways to do this. And I'm not an expert on this by any means, but apparently there is a way to accomplish some kind of error correction if you group large numbers of qubits together.
Interesting.
But it's certainly not a done deal by any means. And there are a lot of people out there who are a lot smarter than me and who know a lot more
Oh,
about
I
quantum
doubt it.
computing. Yeah, no, and take
Hey,
my word for it.
I'll put my money on you any
Guarantee it.
day. If there was a problem in the world of quantum, I know you
Well,
would solve it.
well, thank you. But for quantum computing, I certainly will defer to other experts. But these people have written articles, and many of them are skeptical that quantum computing will ever work as a practical commercial enterprise. It certainly is a very interesting lab experiment and a lot of great physics and a lot of money, billions of dollars is being poured into this every year. Because of the potential promise of quantum computing and its ability to crack codes specifically. That's where a lot of the
Well, it's the factorization numbers. That's what it does really well.
right.
Right? I mean,
That's
the ones that are available today, that's what they do. So you heard
right.
it here.
And that was the whole idea right from the start. That was the
It was.
original impetus to get into quantum computing, especially by the government, by the defense and intelligence establishments, to have this ability to crack codes, which is the same thing as being able to factor large integers into their primes. And that problem is something that quantum computing is well suited to do if you can get it to work. So that's
right.
why there's all the interest.
Yeah.
But like many other things in the technology world, it it the barriers that need to be overcome are simply too daunting, and we just don't have technology today to be able to do it. Not that
So
it
now I
can't be
am
commercially.
hearing grumblings, and so I could be wrong, but you hear things in the industry because it is a very small community, and when you get into that community, you realize just how small it really is. But now globally, I've been hearing a lot of chatter that both China and Russia have made major advancements in the realm of quantum, and they are significantly far ahead of U.S. efforts. And that is concerning to me, and especially when you've completely nailed the reason why billions are being dumped into these machines. Um, what I'm hearing is they've actually got them working right now. So, if that's the case, what does this mean? What does it mean to the world? I mean, do we see a technology balance of power shifting away from the U.S. and now into other countries that would maybe have dominance over us? I mean, do you feel like we're at a point with these types of technologies that maybe we're falling behind, or do you feel that we're still ahead of the game and we always will? What's your thought on that? Because I know China has
Yeah,
dumped bajillions into these
right,
types of technologies.
right. Um, I don't know that I don't know that I don't think I would say that we are falling behind. And I'd be careful not to be too impressed by just the simple fact that they're pouring a lot of money into it
Oh, for sure.
and claim that, I mean, I'm sure they are, but I don't think that well, you never know, I guess, what's going on in the back room. But again, and I think especially in the realm of quantum computing, it's not just a matter of pouring a lot of money into it. There's some fundamental physics which are
Sure.
going to be difficult to overcome, no matter how much money you put into it. And not every technology is worth investing in, even if it could be done. I would
Sure.
give you an example of like the supersonic transports. The Europeans developed the Concorde. Back in the 70s, and Boeing at that time did a study, and they concluded that it wasn't worth it, that it could be done, but it wasn't economically viable.
Sure.
And here we are many decades later, and sure enough, what they predicted came to pass. Concorde was always a money loser. It was never a viable technology. And I wonder if quantum computing might fall into that same trap. You might be able to get some machines working, but will they work well enough? Can they crack codes? And by the way, even if you did get a quantum computer working, why couldn't you use that same computer to generate codes, to generate new cryptography? So it's always easier to make codes than it is to break them.
Sure. And now when you talk about factorization, so, again, quantum, is a threat and one that I do believe will come and could be there now. We just don't know, like you said, what's behind the curtain. But on the other side of it, you have hyperscale computing, which was just announced, which, for those that don't know what that is, that's basically a computer that can do over 1,000 quadrillion calculations per second, and that was developed by Cray supercomputer. So do you feel that the classical computing models are going to, in a lot of ways, catch up to what a quantum computer can do just using classical architectures? Because, I mean, to me, both of them, whether it's a quantum or a classical computer, they're still running the same algorithms that are factorizing numbers and able to break encryption. So knowing that we're at that point, that tipping point, maybe we're looking at the quantum computer more as a very specialized type of computer that will just work on specific types of calculations, but most of what normal people will ever use would be in the realm of classical, but more modified versions like the hyperscale computer. I mean, do you think that's kind of where it's going to go, or are we really looking at, because here's my only concern with quantum, truthfully, and just as we're speaking about quantum computing requires just a boatload of energy to run. And I just don't see the world having a quantum computer on their desk. And these things are like, what, 15 million a piece just to like D-Wave, for instance, is commercially selling quantum computers now along with IBM. But, they're 15 million a piece. They are very tuned for specific applications, which we know what they are, breaking codes. But I mean, do you see where these two things are going to diverge? I mean, is it really just still going to be classical computing, but just done differently?
Well, I don't think classical digital computers will ever be in the same realm as quantum computers could be. Quantum computing is an exponentially more powerful machine, and
Sure.
there really isn't any overlap there. Um, and like you said, if they do get them to work adequately, then I think they will be used for very specific tasks like breaking codes. And but most of what we normal people will need in our lives will be more than easily met by traditional digital computers.
Sure. So now this kind of moves into an area which is, talking about the future and what are some technologies and things that are happening. And one area that you're focused on right now is around, and I had never actually heard the term. Now I've kind of heard of a different term, but you had kind of a cool slant that I'd never heard, scavenging technology. So what is scavenging technology? And now what I knew it as are, little kind of microprocessors, but I think there's a completely different word for it called energy harvesting technology. But um, scavenging technology, you got to tell us about what it is because it's really
Oh,
cool.
it's. I think you said the synonym to energy harvesting, energy scavenging. So this is technology that can be used to um, take waste heat, for example, and turn it directly into DC a DC voltage, kind of like a solar cell, but for heat instead of light. And there's a lot of waste heat around.
Yeah.
Most industrial facilities, power plants, even things like car engines. I mean, all of these things are potential candidates for a very, a cost-effective energy scavenging technology, which is what I'm working on right now with there's a startup based out of Colorado called Red Wave Energy, and those are the guys I'm working for presently, and we are actively in the lab trying to build prototypes and
Wow.
demonstrate the technology. So we have high hopes and fingers are crossed.
Yeah, yeah. So what would be some applications for this technology? Like what would you see as the big market driver for it, and what problem would you be solving?
Well, it would be initially large industrial facilities. I think power plants is probably
Yeah.
the first pick. There's a tremendous amount of waste heat that just goes up the smokestack. So the thought here is to have this device, which is passive, by the way. It's not powered. It's just sort of like it would. The vision is to have films of this sheets of this material that you could line, for example, the inside of a smokestack, and it would cool the exhaust as it goes up the stack and generate some DC voltage, and it would be a way to recover some of that energy.
Wow.
But that would just be the first application. Like I said, there's lots of other applications that could be used as the technology matures and progresses. Any kind of internal combustion engine, in other words, most cars, could have this as well. And there's lots
Wow.
of other heat sources around. And there's a lot of energy there that can be collected and then reused. And it's nice to have it in electrical form too, because it's easy to transmit and store and things like that.
Interesting. Interesting. Well, and I know that there's other devices that can live off of, I mean, there's other ways to capture this kind of energy from, solar power, wind energy, kinetic energy. And do you feel that kind of the next wave as we're moving into this world of Internet of Everything and the Internet of Things, that the things can now be powered by these, I mean, you have many different power sources that we're not even really leveraging. And do you feel this type of technology is really the answer to that, of really being able to have devices that never turn off and are always on and are powered just by nature, basically? I mean,
Yeah,
is that a reality?
that's a good point, and it certainly could be. I think I see where you're going with that.
Yeah,
Just if you can have devices that aren't plugged into any power grid, but
right.
have this scavenging tech around them that can just absorb energy and generate a modest DC voltage just from the ambient heat in the atmosphere or around it. And I suppose that is possible to do. It's certainly not our first vision. It's probably not the first thing that'll get done, but it is
Right.
certainly possible, and that's actually a very good point. I hadn't actually considered that as a possibility, but I think it's a valid point. It
Yeah.
it, it might enable placing devices anywhere and just being able to have those devices be powered just from the
Right.
ambient energy, the ambient heat around it.
Yeah, yeah. Well, I recently heard about some engineers that were actually working on a way to power your cell phone just from the actual signal that you receive, which is, I mean, who thinks of that? But I thought it was just
Yeah,
genius.
yeah,
Um,
right.
but it is interesting, just there is we literally live in an abundance of energy, and I think Nikola Tesla did an amazing job of showing the possibilities of just this limitless energy that we can tap into. We just need to know how to do that, and I think at least it sounds like you're on the way to solving some of those problems with what you're working on that could be really interesting. Um, so now that we're kind of talking about energy and we're talking about the intersection of energy and chips and quantum and all this great stuff, as we move into higher performing computational capabilities, and how do we conserve energy? Because you know we do live in an abundance of energy, and again, if we can start learning how to tap into that, I mean that's an incredible feat in its own right. But we're also at the same point expounding a lot of energy. I mean, we just look at the data center crisis in the world and how much pollution is being derived from them. Um, how are we designing the next wave of chips and technologies that will conserve energy and prevent the creation of pollution? And do you feel that as we move into the future, we're going to be able to start getting more energy efficiency? But see, that kind of goes against physics, right? Because the faster something becomes, the hotter it becomes, the more energy it requires, et cetera. So ultimately, energy creates pollution at some point, right? So,
Sure.
but do we feel like there's a way to start getting to more energy efficiency in the designs and the chips and the things that we're making, or really, if we're going to get to that high performance paradigm, it's just going to mean more energy?
Well, yeah, it's a very good question. Uh, what we need to be able to do is be able to do computations, obviously, with that comes down to just having a better transistor.
Right.
Packing transistors together doesn't help that. If the transistors themselves are not that efficient, they'll burn more energy.
Right.
So it's not a solution.
Yeah.
Excuse me.
So it's really not a linear. I mean, it's going to require advancements, basically, right?
Right. It will. And that is something that I do think about a lot, is how to make transistors better, more efficient, and certainly making them smaller helps. But really, what it comes down to is you got to figure out a way to run
Right. Right.
up against now. Is it gets very difficult to operate a conventional CMOS transistor below about 1 volt. It can be done, but the if you look at the improvement in power supply voltage that runs the transistor, over time, it's very modest increases. For a long time, those voltages were up right about 1 volt. It might be a little bit less than 1 volt right now, 0.9, 0.8 volts. And the power scales as the square of the voltage. So if you're serious about wanting to reduce the energy and the power that's dissipated by these chips, you've got to figure out a way to run these transistors at a low voltage, and the lower the better, of course. And
Sure.
that's where, um, just to get back to what we were talking about earlier, that's where I think cryogenic computing might help a lot. We talked briefly about quantum computing and how that's very cryogenic, down at 0.01 Kelvin. But I'm wondering if there, and this is kind of my personal thought here, is that I wonder if there isn't an intermediate step that we could take down to, say, 100 Kelvin or 77 Kelvin, right around liquid nitrogen temperature. And if we could optimize transistors and chips to run at, I think there's a possibility there um, for being able to get a lot more bang for your buck. In other words, have a lot more computational power for less energy. And I would include there and that includes, of course, the energy required to run the refrigerator to keep the chips cool and
Right.
cryogenically cool. And it's not being done right now. Obviously, we don't have cryogenically cooled desktop computers, although there have been some attempts made over the years.
Wow.
There was a startup in
I
Minneapolis.
tried
It
it
was
once.
called, yeah,
We-
you might have heard of a company called ETA. I believe it was ETA. They were a company that based here in Minneapolis. They built a computer that was a liquid nitrogen cooled machine, and it was impressive at the time for the speed that it could achieve. But it was a very first attempt, and the chips that were used in this machine were not the chips themselves. The transistors themselves were not optimized for low temperature operation. They were designed and built for room temperature operation. They were basically off the shelf parts that were just dunked in a big bath of liquid nitrogen, and sure enough, they ran faster, as everyone knew they would, but they really weren't optimized to get every last ounce of power and speed performance at the low temperature. And that, as far as I know, no one's ever done.
Interesting. Well,
Transistor.
I think that's going to be an interesting area to see where that goes, and who knows if it's going to be viable for more of a mainstream, which I don't think so. But I know back in the early days of overclocking and trying to reach the highest possible thresholds within a CPU, all we were really doing was just throwing more voltage to the processor, trying to keep it cool, and using all different types of techniques to do that. And then, of course, we landed on, well, why not just dunk it in a dielectric, and why not be able to reach those thresholds, using a fluid that can absorb the heat, transfer the heat really well. Then we started working on some, interesting interface materials to put on top of the die to absorb that heat and wick it off faster. Graphene, proved to be a really good one to do that, and we have some patents around that. But ultimately, to your point, that heat becomes dealing with that heat becomes the big problem once you get into more performance and more power. And it's interesting to learn, again, I wasn't aware that the transistor level is really where the problem is, in the heat and how to manage that better. Um, well, I have no doubt, John, that you will solve this problem. I have no
Well,
doubt.
that would be nice. I do have some ideas that I've been thinking about for many years and trying to pursue. And there are a lot of there are a lot of interesting things that happen if you take a conventional transistor, a conventional MOS transistor, and cool it down to cryogenic temperatures and take careful measurements at low voltages. You do see some interesting effects, and especially if the transistor is architected in a certain way. And one of the architectures that I've looked into a lot of is these metal source drains, so-called Schottky MOS transistors.
Mm-hmm.
Instead of doped silicon to uh, build the ends of the device, the source and drain, you get a lot of interesting physics going on there. And I think it's possible that that particular architecture of transistor, the metallic source drain Schottky MOS devices, especially when they're operated at low temperatures and low voltages, might offer a way forward for us to develop a logic technology that can be run at low voltages, less than 0.1 volts, and still be able um, to to perform logic operations at very voltages as long as they're cryogenically cooled. So that's actually something that I'm very interested in, and I
Yeah, me
think might
too.
offer some promise. And it's not such a quantum leap, so to speak, as the current qubit approach to quantum
Right.
computing, but there might be other quantum effects that we could take advantage of that are not quite as dramatic and quite as sexy as a qubit approach, but there's other resonant tunneling or perhaps even superconducting uh, phenomena that we could take advantage of in these metallic source drain devices. So
Interesting.
that I think is a very interesting field, and I think
Yeah.
that kind of would have a much better chance of making it to the commercial marketplace than the qubit-based quantum computers that everyone's talking about now.
Yeah. So now here's an interesting thought, because I mean this is a problem that we had when we did some of our own testing around liquid nitrogen and getting into these lower temperatures. We ended up getting a condensation problem. And I think, as you know, if you have one part of it, of a computer, the chip area, that you're, getting to these extreme cooling temperatures, obviously the stuff around it, condensation builds up, right? Because the temperature differential. Would you see a fully cooled system, where everything is just cryogenically cooled, or how would you isolate the chip so that you don't get these condensate? Because, as you know, condensation will ruin, the other components very easily.
Sure.
So what would you say around that? I mean, are we going to have to create a whole different way that we design the computer, or the chip architecture itself to
No,
isolate, or what would you do?
no. I don't think you don't want to, just in general, you don't want any
Yeah,
more trouble than you need.
that's
So
right.
you only want to cryogenically cool the parts that absolutely need it. So this of course would be the computation engine itself, the CPU, or maybe even the GPU, the graphical processor units. Um, those elements, those chips that are the workhorses that do the actual computation, those are the parts that need to be cooled. You certainly don't need to cool everything
Sure. Well,
else.
but I'm just saying that, the problem is outside and around that, you have the normal chip architecture,
Yes,
and that gets exposed to the condensation, and that's what creates, shorts. And I learned that the hard way.
sure.
So I ruined an
Oh yeah.
entire motherboard doing this. So that's
Oh
why
yeah. Well, yes. And
it got expensive.
it's it's an engineering problem. I think it's a
Right.
solvable problem. Um,
That's good.
and by the way, one of the things I've learned, kind of dabbling around in the world of cryogenics, is that our refrigerator technology, including cryogenic refrigerator technology, is very mature and very stable. Refrigerators, even cryogenic refrigerators, are basically old tech. It's
Right.
compressors, it's copper tubes,
Yep.
it's, welding things together. This is all low tech, old tech. This stuff works forever. If you've ever had a refrigerator that you want to get rid of, but you can't because it just keeps on running, good example. These closed loop refrigeration cycles, even in the cryogenic realm, work well, and they require virtually zero maintenance throughout their entire lifetime. So the technology for the actual refrigerator itself, even for cryogenics, is mature, it's low cost, it
Yeah.
requires very little maintenance. So that's good.
That's really good.
But
Yeah.
but there are, like you were getting to, there's a lot of challenges left that I think are just good old, what I would
Just
call good
design
old fashioned
challenge.
engineering
Yeah. Yeah.
design challenges. How do we prevent condensation? How do we make sure that that the entire chip, not just part of it or not just the one side of it, is cool? How do we flow coolant past the chip to make sure that that the entire chip stays cool? Those are all very interesting problems, but I believe those are solvable. There's no fundamental physics problem. We don't have to discover any kind of new quantum effect or anything to solve this problem.
Sure.
This is good old-fashioned engineering, which
Right.
I'm sure can be done.
Yeah. No, this is really awesome. Well, so let's talk about another area that, is kind of near and dear to my heart. I'm really, I'm crazy about security and making sure that we're protected, and you and I both know that a lot more goes into the chip architectures than what most people know, and as well, I think most recently articulated by the Supermicro disaster, where the little teeny hidden chip was inside of the chip architecture and was able to siphon off data off of every server sold. And so security becomes very important. And also, recently there's a new operating system. Well, it's not new, it's been around for a long time, we found out, called Minix, that was built actually into the chips themselves that Intel was selling, and was a kind of a Linux-based operating system that had a lot of capability to it. So, how do we know as we move into the future that the technologies that we use are secure, that we actually know what goes into them, and that there's some form of a vetting process that gives the consumer confidence now that in the tech that they're buying is protected? I mean, how do you see that transforming? Because, as you're designing these things, we also have to be looking at how do we secure them at the same point. And is security even possible at the chip level? I mean, is it even possible?
Right. Well, I'll start out by saying that when it comes to operating systems, I think there is a way. When it comes to software and operating systems, there is a way to be fairly certain that you're safe. Of course, OSs like Linux, you can use that with some confidence that it's there isn't any malware in there. Any software available out there that's open source, like Firefox as a browser is open source. For messaging, the app that I like to use is Signal. That's an open source, very strongly encrypted messaging app. If it's open source, then software, then I think millions of eyeballs have looked at the source code. There's even software that looks at the software to look for malware. And so it would be hard to sneak in some malware there and not eventually be caught. But on the hardware level, when you talk about the actual chips themselves, that's a lot harder to secure, I think. And of course, reverse engineer a chip. You can patterns and extract out the circuit schematics and try to figure out the logic trains and what the various pieces of circuitry are doing. You can do all that. People have done that, but it is a tedious and very difficult, time-consuming and expensive thing to do. So, and I don't think it gets done very often. So I think the bottom line is that if you buy a chip from Samsung or Intel, you don't really know if there's what you said, siphon off data, package it up, bundle it up, send it off somewhere for analysis. I don't know that there's a way to do that. Short of a very tedious, time-consuming, and expensive process of reverse engineering the chip and trying to figure out circuitry
Yeah.
therefore does.
Well,
So
and one of the things that
I'm not.
say that again.
I'm just not. I'm sorry. I'm not optimistic that there's going to be a really convenient, easy way to know that the hardware that we're buying doesn't have some kind of not malware, but uh, some kind of circuitry in there that will spy on you and collect your data. I don't know that there's an easy way to be safe, to feel safe that way.
Yeah, yeah, and I mean this is where I do like open source because open source creates visibility, right? And I think visibility is important to security because I think we're at a point now where if we really want to be secure, we need to really start asking the fundamental questions: what goes into the stuff we're actually using, right? And having visibility. And thankfully, there's some very good tech reporters and people that do look at these things and do find things. Google is the one that basically found the hidden operating system in chips. But you just have to wonder. We need to get trust back because I think technology has lost trust. And to get trust back means we need to do things differently, which means we actually have to build things that are actually secure. We need to build things that don't have back doors. But do you think that Big Brother and government is going to let that happen? Because I mean, when you're given great control, do you want to give that back?
Well, there are
And by the way,
certainly,
we probably shouldn't be having this conversation, but I mean,
yeah.
I
Well,
mean, but
just just don't say anything too controversial,
yeah, yeah,
unless you want to switch. Unless you want to switch the signal, then you can.
yeah.
But well, there's certainly a lot of people in government who would like to have access to all our data. People, FBI and NSA, people looking for terrorists, people looking for criminals. They have a legitimate case to make that they need access to data. Unfortunately, there's also the flip side of if you give if everyone's information, messages, location, etc., is all available, then what's eventually related that's going to fall into the wrong hands or be used for the wrong purpose. So you've got that to worry about. Um,
Yeah, and
but
these
I
are very
think,
interesting
I think,
problems, aren't they? I mean,
yeah, and I think there's you never underestimate the creativity of engineers when it comes to solving difficult problems like this, especially if there's money to be made. So I think that even if there were if there was hardware, chips that we buy from overseas that had malware circuitry in there, I think there are probably ways. It might be hard to detect the presence of such bad circuits. I'll just call them uh, in the chip itself. But there might be some way to solve this problem where you could have other chips, other hardware in close proximity that would be like monitors and watchdogs and could watch data packets leaving that chip, for example.
right,
So
right. Yeah, I've had some ideas along that line where, I was really thinking about, how do we create a monitoring system that will allow you to know, what's coming, does what's coming in and out of your processor match what task or thing that you're doing is, right?
right.
And so, that was an idea that we kind of had. And but one of the things is, there is this dilemma on, one hand, and you said it so beautifully. We have to protect our country, and I do believe the government has a role in looking at information and trying to find terrorists and trying to find bad actors, without question. But there's also the other side of it is we're a country of laws and due process, and you're innocent until proven guilty, and you have a right to privacy. And so, you know, you either have privacy or you don't. And so we're really facing some ethical dilemmas as a culture and as a country and a world, and we have to just ask ourselves, what kind of world do we want? And um, and the question is, do we really want to invest in technologies that get us to 100% security when we have forces around us that don't want that? I mean, Does the government really want to be secure? I don't know. You know what I mean? And do Google, Microsoft, and Amazon really want you to have complete security of your information? I don't know, because their models kind of break apart if they don't have access, right? I mean, if you were really
That's all very
secure,
true.
you know, you know what I mean?
Yeah, sure. It's all very true, but at the same time, individuals like you and me, we want the security. So,
Right.
um, the fact of the matter is that certainly in the software realm, it's well nigh impossible to prevent people from having the privacy and security they want. There's you know, the all the technology for encryption, the algorithms and the techniques are all very well established. There's lots of freeware out there that provides very strong encryption, which essentially cannot be broken, at least not until quantum computers come along. So privacy is simply a fact of life right now, at least in the software realm. There is as we've talked about, the lingering question of, well, what about the actual hardware itself, collecting your data? What's to say that some chip in your iPhone or in your Android phone that is recording every keystroke that you make, and therefore has access to all your information, passwords, everything. What Who's to say that that chip isn't there? Well, we don't know that. I don't think we know that. And I don't know that there's a way to know that. So
Yeah, I mean, you can get
we,
paranoid very quickly, can't you?
yes, you can. And
And,
you got
and,
to be
and by the
careful
way,
not to think
the
about it too
more you
much.
get, yeah, well, and that's the thing. The more you get into technology, and the more that I've learned, and the more we've been developing technology and building. I mean, I built stuff at the chip layer. You built stuff at the chip layer, and you start to get really paranoid really fast because there's so much that goes into the things we make that we don't have any control over, right? And as technologists, when you start asking those really hard questions and you can't get an answer, it gets a little frightening, right? And especially when you're an advocate for privacy. And so I don't know, we're on a slippery slope as a world, and I think hopefully we can reach a point where we can solve some of these problems. But you talk about the quantum security and getting to a level of security. The way I view it is zero trust. I don't trust anything. I don't trust anyone. And so we have to build our systems and technologies with a zero trust. And I think, at Secured2, that's how we've looked at it is, first of all, let's get a technology that can't be factored. That's what we've developed. Let's try to get to a technology that is based on identity. So I really know it's you to unlock the information. But, let's be really honest. Once you unlock something, the computer you're on has access to it. And if you can't trust that computer, that data can be siphoned, right? And so where I'm getting really concerned is how do we start blocking the holes in the architectures? And that's why having, great conversations like this with people like you is that it's hardware and software, right? And at least I've solved the going over the internet security problem and the at-rest data problem. Now the next problem we got to figure out is this endpoint and the actual
Right,
device, right? Because
right,
ultimately something's going to unlock it, something's going to touch it, and once you do that, that device has access. And if you can't
right.
trust the device,
Yeah,
you know what I mean?
yeah.
So
No, if there's a chip in your laptop that is recording everything that appears on your screen and
that's
records
right.
every keystroke that you make, it doesn't matter that the information got to you in a very encrypted form, because the minute you, like you were saying, the minute you decrypt it, now your laptop, your device, your phone, whatever, your tablet has access to it in the unencrypted state, and
That's right.
you're toast at
That's
that
right.
point. So,
Well, now, not
but
now. Now, I will say this
yeah,
one thing, and in fact, I just had this conversation with a client who's dealing with some very interesting data. So one of the things that I've been talking to him about is, he needs to create a perimeter where when you do that unlock, and this is really where I think my company, where I've looked at is push all the risk to the endpoint because I can manage that endpoint, right? I can build the castle wall really high, and I can put an iron gate, and I can monitor things, and I can really protect that endpoint. and I can open up the device and unlock data in that device if it's behind protected barriers. But if that person's in a coffee shop or at home or whatever, I lose all that capability, right? And so that becomes the challenge. And and it's a problem that hardware is going to solve, but we're not there right now, are we? I mean, really?
No, no, we're not. And you know, in software, we can solve this problem by making software open source, and that effectively provides a guard against any kind of malware making its way into the software. Um, and so I guess the question I would have is there an equivalent way of doing things in hardware? Is there a way that we could, if
That's what
Intel
I'm
comes out
looking
with
at.
the next
Yep.
chip or Samsung comes out with their next chip, is there something, an open source equivalent somehow? And I really don't know what form that would take, but something that that the user community could look at and verify and say, yay, verily, this chip is good. There's nothing bad in there. It's not going to spy on you or do anything to your data. It's good because we have the circuit schematic, we have the logic
That's right.
tree, and so we know exactly what all the transistors are doing, and there's nothing bad going on. I wonder if there's a way to do that, to sort of have an open source equivalent for hardware.
See, I mean, this is what I would like to see. And actually, it's interesting. I've had this discussion with Foxconn, one of our partners, and so we're looking at actually building our algorithm for protecting data right into the chipset itself. And so literally, we would have an ASICs chip, and our algorithm would be in it, and all data would be processed, being written to storage or being processed would go through this algorithm. Now, the problem is, and you know this, is that ultimately you have to have a chip. And since there is no open source standard around chips, we don't know what's in that chip, right? I mean, at the end of the day. And so one thing I would hope, and I'm glad because I have many people from Intel that will probably be listening to this podcast today that are friends, and um, how do we get Intel to step up? Because we have a brand new CEO. He's awesome. He's trying to build the new culture the right way. And by the way, I love Intel. I mean, I've worked with the people. These are very, very good people that work there, and I don't think they've ever had malicious intent. However, their largest customer is government. I mean, they make no bones about it, right? I mean, government is a massive customer, and the government will tell them what to do. So, but do you think an open source is possible, knowing that the government will apply so much pressure on them to put backdoors in for national security reasons?
Um,
I mean, do you think it's
it's
ever
a good,
possible? I mean, this,
well, I think the first question is possible, even if everybody was rooting for it, even if everybody wanted it, government included, even then, is it possible? Um, and I don't know. I don't know what the
yeah,
answer is.
yeah,
I think if it was possible, I think there'd be a huge demand for it. And I think if the word got out that there was a way to make these chips in a such that you could be guaranteed that it's not spying on you in any way, or there's no back doors or anything like that, I think the demand for that would be huge, and
yeah,
that
I
would
agree.
be a market force to be reckoned with in and of itself. And I think
I agree.
Intel and the Samsungs of the world um, would respond to that market force. There might be some people in government that don't like it, but that would just be another force, and there would be a tug of war, a push and pull, I suppose. But I think that the people who want the privacy and the security would ultimately prevail, just like they've ultimately
I agree.
prevailed in software and
Right.
in the enormous number of very secure messaging apps that have very strong encryption, which is basically unbreakable. And that was opposed when those things first started coming out. I believe in the 70s, there was a piece of software called Pretty Good Privacy, and
Yeah,
that
yeah.
was
I
the
love
NSA
PGP. Yep.
yeah, they were against it. They tried to slow it down, shut it down, and they ultimately lost. Uh, and
Right.
and and now we have Signal and lots of other messaging apps that use end-to-end encryption, and it's basically now just a fact of life. And I suppose the NSA and the FBI and everyone else, all the other government agencies around the world, have just had to come to terms with that.
Right.
Similar would happen in the hardware realm if there was a solution.
Right. Right. Yeah, and and I when I looked at when I started this company, the problem I saw was just it wasn't really necessarily the brute factorization of the actual encryption. It's actually attacking the random number generator that creates the key, right? That's what the hackers are exploiting now. And so that's why I just lost all trust in any math-based solution, encryption solution, and that's why we went in the direction we did. But it is interesting because, I think the government has not been able to break signal, and they've allowed it to persist. And we haven't had anybody with earpieces showing up at our office yet. So obviously our security is, you know, they're letting us survive, which is nice. But it's interesting. So I think hopefully the right things occur, but I think it all starts with a conversation, and I think this type of a conversation is a good one to have. But I'll just tell you, thank you so much for what you've shared today. This is exactly the kind of conversation that our listeners like to hear, and we definitely have to do this again because I think there's a lot more we could be talking about. But I feel for an open volley, this was a great one, and I think we've covered a lot of ground today. So just thank you so much for doing this today and taking the time.
Sure thing, Daren. It was my pleasure, and enjoyed the conversation, and I look forward to the next one.
I can't wait. Well, have a great day, and thank you everybody for listening today.